Greetings. As we continue to explore proof, I want to remind you of the last thing we showed was that, sorry, wrong thing. That we showed though is that the geometric mean was less than or equal to the arithmetic mean. We're actually going to talk about a different kind of mean. I'm going to call this geometric and call this arithmetic right now. But we're going to talk about a different kind of mean. And this mean occurs in a different scenario. And here's the scenario. You might have seen this before. If we travel d miles or d distance at rate 1 for a certain amount of time, and then we travel that same distance at rate 2 for another amount of time, what we want to do is figure out what's the average rate that we traveled. And let's see, we'll call that, I'll just put a little find average rate. So this occurs when you're doing a round trip and you go, let's say you leave home and you walk to the store and then you get a ride back. And what was your average speed the whole time? Well, we're going to let R equal the average rate. And some people might say, well, it's the average of the two rates. And well, that doesn't account for everything. It doesn't account for the fact that you spend more time at the slower rate than you do at the faster rate. So if I say t1 is equal to distance divided by rate 1, and if I know that, furthermore, I know that the rate is equal to 2 times the distance divided by the total time, since rate is equal to distance divided by time. And if I put these two facts together, then I can get 2d over d over r1, plus d over r2. And if I multiply the numerator and denominator by, well, you can see we can actually clear the d's out and just make it 2 divided, sorry, I should make that in equals. Make it 2 divided by 1 over r1 plus 1 over r2, and then multiply by r1, r2. I'm going to get 2 r1, r2 over r1 plus r2. Actually, r2 plus r1, but the same thing. So this is the average rate. That's the rate that accounts for the fact that I actually spent more time at the slower one than the faster one. And this is there's a definition for this. This is called, I'm going to do this, this is Hindersman style with the DEFN. This is called a harmonic mean. It's actually defined as 2xy over x plus y. If you want to find the harmonic mean between x, y, that's it. And so there is an interesting thing that happens, and this is actually a corollary of a previous proof we did, so I'm just going to call it a corollary, where I know that 2xy, oops, let's delete that for now. I don't want to reveal it just yet. But we said we knew from before that the square root of xy, the geometric mean, was less than or equal to x plus y over 2, the arithmetic mean. And it turns out that the geometric mean is also greater than or equal to the harmonic mean. The harmonic mean is the smallest of the three. Now these could all be equal to each other, but we know that this relationship holds true. And we know that because we already know this. So if I start with this, xy is less than or equal to x plus y over 2. If I start with that, and I multiply both sides by a factor, you can probably look at this and start to determine what that factor would be. You can actually slide this over and get this other result, which is something that I find extremely interesting, that you can actually just multiply by this factor, which happens to be 2xy over x plus y, radical xy. And if you do that, if you multiply this by that, you're going to get, let's see, the radical xy's cancel, and you get 2xy over x plus y. And if you multiply it by here, you get the x plus y's to cancel, and you just end up with, let's see, you get the xy's to cancel, and you get the 2's to cancel, And so you end up with xy over radical xy, which clearly you can see is actually the same as radical xy. So that's it. That's actually proven it. We took a corollary, and by a simple factor of multiplying both sides by something that we kind of created, and we created that because we can. We can just kind of, I know it seems weird, but you actually can just pull that out and start to stick it in. And if you look at the properties that have to hold true, we know that x and or y can't be 0 in this. So that's a limitation. But it's something that is not necessary in the final result, so we can kind of play around with it and work it that way. So that one's done. Okay, that was a leftover from before. I didn't want the previous notes to be too long, nor do I really want these to be too long, but this one's a little bit longer. So the next thing, the next definition, we're actually going to talk about sets. We're going to talk about sets a little bit more generally than you did before, although both of you should have had finite at some point, or I guess it was discrete back then. And elements of a set. So when we say this is just a notation thing. That means that x is an element of set A. And we oftentimes represent a set in just kind of a little blob. Doesn't need to be specific. And this means the opposite. That means y is not an A. Y is not an element of set A. So I'm just trying to introduce what those symbols mean, because we're going to use those symbols a lot. We should actually be able to write a lot of math without writing a lot of words in this advanced stage. So this is just some more ways to say this. If set A is defined as just the two numbers -1 and 1, then 1 is an element of A, which means 1 is contained in A, 1 is a part of set A, and -1 is a part of A, an element of the set. So that's the definition of set. Now let's talk about subsets. If every element of A is also in B, we say A is a subset of B. And it's written like this. A is a subset of B. So some examples of this that go to things that you should remember. I know that the natural numbers, remember the counting numbers, 1, 2, 3, 4, 5, 6, that is a subset of the whole numbers. And that's a true statement. But we know that the whole numbers is not a subset of the natural numbers, because the number 0, which is a part of the whole numbers but not a part of the natural numbers, makes that not true. I wish we could do set theory earlier, because I could say this, that the natural numbers is a subset of the whole numbers, which is a subset of the integers, which is a subset of the rational numbers, which is a subset of the real numbers, which is a subset of the complex numbers. And all of those hold true, that you keep building up your sets. And you might be curious, and I'll just kind of lead into this, there are an infinite number of complex number sets that we could keep going. This is just one of them, so that's kind of a neat thing. One of the things now we're going to have to define is if two sets are equal. Two sets equal, just to give this a name. A is equal to B if and only if. And it might be time to kind of kill that word a little bit, because that also has a mathematical symbol. And it's just a bidirectional arrow. This means if and only if. It means if something's true, then the other's true, and vice versa. It's two directions. It's a very strong statement in math. If and only if A is a subset of B, and B is a subset of A. So you kind of think about subsets as being smaller sets. That's not true. They could actually be the same set. This is an interesting thing. To prove that two sets are equal, you have to prove both ways. You have to prove A is a subset of B and B is a subset of A. So that is kind of a definition there. So let's see, a trivial example. And I really sometimes had to rack my brain for this word trivial, because a trivial example is one of those examples that's just kind of a duh example. We all know it to be true. We don't need to prove it, but it's just an obvious 1. It's almost definition. Trivial example is that A is its own subset. And also the empty set is a subset of any set. Because nothing is a part of the empty set, so nothing is also a part of that. I mean, you just have to go with that one. And if you don't want to go with that one, then we have what's called a proper subset. A proper subset is any true subset of A other than A. So it's not the same set itself. And we also have this thing called a power subset. A power subset is the set of all possible subsets. You actually dealt with this before when you did permutations and combinations in probability in Algebra 2. We didn't quite call it this, but we sort of dealt with this concept of a power subset. So how do we do it? Well, the power subset of the set, again from before we got the set -1, 1. Power subset would be the empty set. It'd be the element -1. It'd be the element 1. And it'd be the element, both of them, -1, 1. So it's all possible subsets. There's some other little things that appear in terms of sets, just wants to know. We have elements that are not in a set, Q prime, and we could argue that Q prime is equal to the set of real numbers minus the set of rational numbers. Q prime is what we call the irrational, equal to the real minus the rational. We can have symbols like union. If I have Q prime union Q, then that's equal to the real numbers. That any element that's part of one or the other of them is equal to the real numbers. I'm not going to belabor a lot of the union intersection. You should remember that. And then furthermore, if I have Q prime intersect Q, that would just be an empty set, because every number in the real numbers has to be part of one or the other. And there's not, or let me rephrase, there's nothing common to both of those. So let's do an example of this. Kind of looking ahead, and there are only 2 examples left, but they're going to take a little bit of time. So buckle down. This would be a good moment to pause if you're going to come back. Just come back to this, but I would do these 2 examples back to back. Okay, here we go. We're going to let S equal all x in R. This means all real numbers. It's kind of a conditional statement, such that, or you can draw a vertical bar down. I tend to prefer the colon. I don't know why, I just always learned it with that. Seems cleaner. Such that x squared is less than x. Okay, freeze for a minute. Let's think about which numbers are true. Which numbers are whose squares are less than the original number itself. Because there are a whole set of numbers that are like that. If you square them, they're actually smaller. Those are the fractions. You should think about that those are the fractions. So that's kind of where this is going. We're going to let set t be equal to all x in R, such that 0 is less than x is less than 1. So you kind of thought about, okay, so it's the fractions less than 1. Why do they have to be positive? Well, they have to be positive because if they're not positive, then it can't possibly be a positive number less than a negative number. So these are the positive numbers between 0 and 1, the positive real numbers. And so what we're going to do with this example is we're going to prove that these 2 sets are equal. And this is going to be an illustration of how to show this. Not just intuitively think it, which we've been used to doing, but actually to show it. This is not a geometry 2-column proof. This is a written out mathematical explanation of reasoning. So in order to prove S is equal to T, we have to refer to the definition and prove 2 things. First, we're going to prove that T is a subset of S, which strictly speaking means if you find an element x in T, then x is also an element of S. So we have an if-then that we're going to now prove. So I'm breaking this down into smaller steps. So what does it mean? If x is an element of T, then I know that x is less than 1. Okay, we know that. X is actually greater than 0 and less than 1. But if I just say that x is less than 1, I have a very good result. We can multiply both sides by x, and then I get x squared is less than x. Now, why didn't the sign switch? The signs didn't switch because x is greater than 0. X is positive. So I can multiply both sides by x since x is greater than 0. And since x is greater than 0, again, the signs don't switch. Okay? That's it. We just did it. We showed that by one simple step, multiply both sides by x, I got the result that x squared is less than x. So that means x is an element of S. We need to say that. And then I say one more. So, since if x is an element of T, then x is an element of S, that means T is a subset of S. And I've proven the first part. Next, we're going to prove that S is a subset of T, meaning that if x is an element of S, then x is an element of T. Okay, so just checking my time. 15 minutes. Sorry, I told you this was going to be a little longer. But you only have to watch one of these a week, so get over it. Just checking my layout. Okay, if x is an element of S, then we know x squared is less than x. Oops, not less than or equal to. Less than x. Okay, this is a little tricky one, but it's not terrible. What I'm going to do is I'm going to subtract it over, then I'm going to factor it. Oops. Sorry, that should be a less than. And if that's true, if x and... There's actually a very interesting thing that this means. This means that x has to be positive and x minus 1 has to be negative. Well, why is that true? Well, think about it. If x was not positive, then this wouldn't work. You couldn't take a negative number and then subtract 1 and have the product be less than 0. That wouldn't make sense. No, 1 needs to be positive and 1 needs to be negative. And x is the one that has to be positive and x minus 1 has to be negative. So what I can do is I can take this statement and then just kind of work it around. X is less than 1. And now I have compound inequality, which means that 0 is less than x, which is less than 1. And so then I've shown that x is an element of T, and that S is a subset of T. And as a final statement, I can say, therefore, S is equal to T, since I showed both conditions. Put a little QED, and we're done. Number 2, the penny problem. I know I keep saying this is one. This one requires some colors, so just be patient with me. This was a kind of cool one that came in the book, and we never did this when I took the class, but I really wanted to do this one, because I think it's kind of fun in a math sense. It's called the penny problem. So we'll see if I can remember and kind of explain this as best I can. Basically, let's say that I have a pile of 1. And then I have another pile of 2. And then I have another pile of 4. And then I have another pile of 2. I'm going to list them 1, 2, 4, 2. And what you're going to do is you're going to take 1 penny from each of these piles. So just take one of these and you're going to create a new list. And when you do that, you get the original 1. You have 3 left over here. You have another 1 from before. And then you suddenly have 4 from before. The 4 that I circled now become a new pile. And if I number those are 1, 3, 1, 4. And so on and so forth. You're going to do that again. And so you take 1 from each of them. And you're left with, well, you collapse piles that don't exist. So you have 2, then 3, then 4. And if you do it again, you have 1, 2, 3, and 3. And then if you do it again, you have 1, 2, 2, and 4, and so on. You can kind of see that there's no pattern really that I'm discerning, but I know you can figure out what you're doing, and you can at least figure out from one how to get to the next. Okay, now sets can be anything. We're going to let S equal the set of piles. I shouldn't say piles. Hang on just a second. Let's call each of these a list. So 1 through 3, 4, 1, 2, 4, 2 is a list, 1, 3, 1, 4 is a list. Let S equal the set of lists that do not change. Thanks, Bose. You just texted me when the homework's due. Tomorrow. Actually today, but whatever. Let S equal the set of lists that do not change. We're going to let T equal... Well, I want to pause for a minute, and I want you to think about what kind of lists don't change. Meaning, as you go from one pile to the next, which type of lists do not change? What would be identical from one to the next? I'm going to pause it for just a minute and let you think about that. So the two words that come to mind are like pyramid or stair step. A list like this. Something like that. And no matter how big you make it, you would always take one and make the new pile, and it'd be exactly the same thing. So that should be kind of something that you think about. We'll say let T equal the set of lists with one pile of each size. Okay. So to prove this, we need some setup. We're going to say let A be a list with n piles. And B is the resulting list. And I just looked and realized I'm missing something right here. Let T equal the set of lists with one pile of each size. We'll say each size 1 to n. Because you have to have one everywhere in the middle there. So if you have n piles, you should have one of every type. That should make sense. That's kind of the stair-stepping thing that we just showed in terms of this increasing style or increasing size. So A is the original list, and B is the resulting list. That's another way to think about it. So for instance, if A was 1, 2, 4, 2, then B is, you can do this one, take one from each, you'd have 1, 3, 1, 4. So think about this as also forming a function of a type. It's a very specific rule of a function. Anyway, as you probably can figure out, we're trying to prove that S is equal to T. So furthermore, one little statement. If A is a subset of S, then B is a subset of S, and B has n piles. We need that to be true. We need the list to not change. So that's kind of clarifying some aspect of this piece right here, what S is. If A is a part of S, then B is a part of S, and we know right away that B has n piles because A had n piles. So I kind of consider this a little setup. We're defining these A and B's. So now let's get to the meat of it. We're going to prove that S is a subset of T. And so I just want you to kind of see how this explanation is, because sometimes you just have to write. And that's the challenge of it. That's the big thing about higher level math. You just have to write. Since one pile is introduced, one pile must disappear. And watch the reasoning here. If one pile disappears, that means that your original list has to have a pile of size 1. So that means that A has a pile of size 1. Now, they don't change. Meaning, like, if you're a part of S, your next list, your resulting doesn't change. So if A has a pile of size 1, that means that B has a pile of size 1. So A has a pile of size 1, which means B also has a pile of size 1. Now, watch the back and forth here. So if B has a pile of size 1, that means that A has a pile of size 2. because that B pile of size 1 had to come from one of size 2. Now, you can kind of see where this is going. This is a sort of preview of a type of proof called mathematical induction, where you just keep building on something that's established. So, you continue for I from 1 to n minus 1. Meaning, this is kind of more written out. If A has a pile of size I, B has a pile of size I. So A has a pile, so A has an I plus 1. Oops. This gives A with one pile each of size 1 to size n. Because if you continue that process all the way from I values from 1 to n minus 1, you get that back and forth, and you finally get that last I plus 1. So, since A has one pile each of size 1 to size n, that was the condition for T, the set of lists with one pile each from size 1 to size n. So, S is a subset of T. Now we do the second part. Let's line this up. T is a subset of S. This one is a little bit, at least less writing. So, okay, just lining it up. Consider element of T. Sorry, I should say an element of T. So we're going to consider an element of T with piles 1, 2, 3 to n. So we just, kind of an arbitrary element, just basically an arbitrary size. For each I from 2 to n, piles become basically piles become I minus 1, meaning that piles become 1, 2, 3, to n minus 1. So that's kind of just a way of saying that for each index from 2 to n, that's why we use I, piles then become the 1, 2, 3 all the way to n minus 1. With a new pile, well, there were n of them to begin with, so with a new pile that has n elements. And the result is the original list. So, T is a subset of S. Then we can say, therefore, S is equal to T. And then put a little QED, or a box, because we're done. So, less problems, but a little bit harder. You're going to do still that first chapter, and you're going to do 13, 16, 27, 30, to 33. And that's due in 1 week. Bye-bye.